Okay, so welcome to the 15th video in the discrete structures series, and this video is going to be about the algorithms for binary integer operations, and this is going to focus on representing integers in their binary formats and defining various operations on them. And the operations are addition, multiplication, division, and modular exponentiation. So in this video, we'll be looking into the concepts of addition and multiplication, and we will be looking into these concepts in the upcoming video. Okay, so let's get into our first topic, binary integer addition. So let me make a note of that, binary integer addition. And our goal here is to be going to be able to write a pseudocode or an algorithm that reflects the process of binary addition. And the algorithm that we're going to use here is going to be the pen and paper algorithm that we already know. So on this side, I'll draw a numeric example. And looking into the example, we'll try to derive what the pseudocode should be. Okay, so let's consider adding any two numbers. So I would take an example of 14 and 88. So when I'm adding these numbers, you should recall that we do it one position at a time. So we add a 4 and a 8, and that gives us 12. And then we carry over a 1 to the other spot. And then on the second iteration, I add not only my digits, but also the incoming carry, right? So 8 plus 1 is 9, and 1 added to that would give a 10. And I would put a 0 here, carrying over a 1, but then the last carry would be a part of my result itself. So this is my normal addition algorithm. So in order to generalize this, I can observe that I've added two numbers here, and this is the first pass, while in the second pass I've added three numbers because this includes the previous carry. But when I want to write an algorithm, I want all of my passes to be similar. I can accomplish that by assuming that the first pass is going to take a carry of 0. So this brings in the uniformity, right? So each time I'm adding 3 digits, generating a sum, and then generating a carry out. Okay, now let's start introducing some variables. I want to call the carry that goes into each stage C. Okay, C is the carry that comes in. So if I'm talking about this first stage, C is 0. So in each stage, there's going to be a sum digit. I'm going to call it a S to denote sum. And there is this carry that goes to the next step, and I want to call that D. So the value of C and D depends on which pass you are looking at. So assuming I'm looking at the first pass, C is 0, sum is 2, and D is 1, the next stage carry. But if I'm looking at the second pass, C is 1, right? Because this is the input to the second pass. And D is 1, and that carry is being included in the result as you can see here. Okay, so we have introduced D, C, and S as we need to. And now I want to write two expressions for D and S because these are the outputs that I need, right? The sum and the carry to be sent to the next stage. So what would D really be? So let's say I'm adding these two things, right? So let's say I'm adding this A and B. And I want to be able to write D and S in terms of A and B. And remember, D is the carry that we're sending out. In this case, 4 plus 8 produces 12. And I want my S to be 2 and I want my D to be 1. Okay, so the next stage carry should be 1. So what expression could you really write here that would produce a 1? So I could say simply add A and B, and also C, right? Because in the next pass, the previous carry is also going to be relevant. So I'm going to add A, B, and the incoming carry. And this A plus B plus C is kind of like the full number 12, right? I'm adding everything, 4 plus 8 plus 0. And in order to get only 1, I want to divide this by a 10, okay? And that will give me a 1.2. And then I want to take a floor of this number, and then that will give me a 1 in this example. Okay, so this is going to be relevant in our pseudocode. So you add all of the terms, you divide it by 10, and then you take the floor. The only thing that will do different is divide by a 2 here instead of a 10, because here we are working with decimal numbers and here it would be binary numbers. So similarly, let's get to S before diving into the algorithm. So S would be, so let me begin with A plus B plus C. And this is 12, right? And this time instead of a 1, I want to extract out a 2. So I can do that by subtracting a 10 from this value. By subtracting a 10 times D, okay? So 10 times 1 is 10. If I subtract that, I'm going to get into this value. And I'm only multiplying by a 10 because I earlier divided by a 10, right? To take the floor. So this expression is also going to be relevant. So please repeat this section if you need to. You need to be clear why D is this expression and why S is this before you can understand this pseudocode. Okay, so let's begin this one. We say a procedure add which takes two positive integers. And in order to do the addition, I need to divide them into individual bits, right? So let me divide A and B into individual bits. I'll assume A is equals to an minus 1, an minus 2, and it goes up to A0. Okay, So this is just a binary representation of number. It's only like saying, let's say 5 equals 101 in binary. So just breaking it into a binary number. So similarly, we assume B, and this is also base 2. Okay, now we begin the algorithm. What did we do first here? We started by assuming a 0 for the initial carry. So let's do that. So let's say C is equals to 0. And I want to start running these addition passes now, and I want to do that for as many bits as I have. So I want a loop that starts from 0, the initial position, and ends on n-1, the final position. So let me say for j equals 0 to n-1, and let me get some space here. And the code that I write here is going to be inside the for, right? It's going to be indicating a part of the loop. So there are two ways to indicate that. I could write a begin and an end whenever the loop section ends, or it is also customary to use just the curly braces, like a lot of programming languages do. But here I'm just worried about the pseudocode, so I'll just use the begin and end notation to define a block. So what do I actually need to do for j is equals to 0 to n-1? So first calculate carry, right? The next is carry, because the sum actually depends on the value of the carry. I'm sorry, I actually covered it. I'm just going to bring it a little bit here. Okay. And you can see here, first I want to calculate a d, and based on d, I can calculate the value of s. So in terms of this pseudocode, I want to initialize and equalize a value of d to all the digits that are being added in this pass, right? And that would start A0, B0, A1, B1, A2, B2, and that is why we have this loop, right? And that is happening with this index j. So I want to add A in index j, and initially that would be this one. Also B in index j, I want to add the previous carry, whatever C is. The first time it is 0. And then I want to divide it by 2 and then consider the floor of that value, just like I did here. And then I can work out my sum. My sum as would be aj plus bj plus c, and again we are working with not decimal but binary here, so minus 2 times d. Okay, and by the way, this is also the current state sum sj. Let me denote it by sj. So you could imagine that there is a sum collector here, and that has its own digits. So 0, 1, 2 up to n-1, right? So every time I assign sj, I'm collecting one of my values for my sum. So the first time I get a S0, and then I get a S1 and S2, and so I generate the digits for my sum. Okay, now I want the loop to repeat and do the same thing again. But before I do that, I want to initialize the value of C for the next pass, because I don't want the C to always remain a 0. I want to set C equals to D, so that when the next pass begins, it considers the correct value of C as the previous carry input. And now I can end my loop. And there is one last thing to do. This sum will actually have not n-1 but n digits. So for an example, the sum of 99 and 24 would have a 3-digit sum because of this carry. And in this example, we have n digits here, 0 to n-1. So this sum should have n plus 1 digits, right? And counting from 0 to n would result to n plus 1 digits. And therefore, the last thing that I need to do in my algorithm, I'll write it here because I don't have space. After ending the loop, what I want to do is to set the nth bit of the sum to the last carry. So as n would be equal to the last generated value for d. Okay, and then I can end my procedure. And this algorithm is used to add binary numbers. So you can conclude this by saying, after this algorithm has completed all passes, all the digits of s would have been accumulated. Okay, next we work into building a similar procedure for the multiplication algorithm. We'll also look into an analogy in this example. But here it is easy to work with binary numbers to begin with, so let's do that. So it's really easy to multiply binary numbers, and we'll collect a few properties to understand this one better. So let's say any binary number times 1. So let's say 10111, a random number. If I multiply this with a 1, I'm going to get the same number. If I multiply this with a 0, I'm going to get a 0. And since this is binary, there are no other possibilities. The next thing that you want to know is what happens when you double a binary number. So what happens if I multiply a binary number into 2, right? I'm just writing 2 in decimal, but understand that this is just a representation for 2. So what happens when I multiply by 10 in decimal? You just add a 0, right? 9 into 10 is 90, and multiply by 10 again, you get another 0. And the same thing happens with binary. When you multiply by a 2, it gets one more 0. So this will be equal to 1010. Okay? So multiply by 2 again, we add one more 0. And let's quickly verify this with the small numbers. So 2 is this, right? This is the representation for 2 in binary. And therefore 2 times 2, 4 would be this. And this would be 8 and 16 and 32 and so on. Okay, so we know this. Now let's look at the third one. Whenever we are multiplying two binary numbers, we can consider one binary number as a whole and only consider the individual digits of another number. So consider I'm multiplying 110 with 101, okay, just two random binary numbers. So my idea is I only need to care about the individual bits of this number. This number I can consider as a whole. It will not be changed, but it will only be shifted, okay. So let's say I'm multiplying 110 with this number. I multiply it with a 1 first, and that gives me 110. See, I did not have to transform this number in any way. And then the second term is a 0, that does nothing. So I'll not even write it here. And what happens with this third term? See, multiplying it with 1 still results to the same number. But since this number is shifted 2 times, I want the sum to be shifted 2 times as well. So this number just gets shifted here, 110, and then there will be 2 shifted positions. Okay, so all that happened to this number was shifted. Here it got shifted 0 places, here it got shifted 2 places. And how many spaces does it need to shift depends on the multiplier's position. So in this case, the position was at the 0th index, so it didn't have to shift. Here 2 shifts, so 2 shifts had to follow. And these things are called partial sums. And the final result of multiplication would just be to add up these partial sums. Okay, so let's start writing this as a procedure. So I'll say procedure multiply, and it takes a, b, okay. And I only need the binary representations for one of these in order to demonstrate my algorithm. So let me just assume b equals bn minus 1, bn minus 2, and all the way up to b0, similarly to what we did in the last step. And this is going to involve 2 steps. One step is going to generate each of these partial sums, and the second step is going to add all of those partial sums to give me the final product. So the first step works by passing the top number through each of the digits of another number. So I need to loop for each of the digits of the multiplied number. So for j equals 0 to n minus 1, and I'm indexing from 0 to n minus 1 here. And let me specify the loop block by writing begin. And the rule is simple, right? If my number is a 1, just use the same number and shift it appropriately. If the number is a 0, don't do anything. I don't even need to add in that case. So if bj is equals to 1, that means my current digit being multiplied is a 1. I want to collect this partial sum. So then my partial sum cj would just be a shifted j places, right? So a shifted j places. Because whatever the position of j is, that is the number of times I want to shift. And if this is not true, otherwise cj simply equals 0. And what does this else mean? The other case when b is 0, right? When I'm multiplying by a 0, my partial sum is automatically 0. But when I'm multiplying by a 1, that is when my partial sum equals the multiplicand shifted j places. Okay, so I'll end my loop here. And doing this, I've collected all the partial sums. So let me move a little bit to get some space here. So at this stage, I can say that C0, C1, and so on are my partial sums. Okay, so I've collected all the partial sums, and you should see this C0 is analogous to this, C1 is analogous to this value, and so on. All I need to do now is to add all the values of C together, and that would be my final product. So let me get a little bit more space here. Let me say my final product P is equal to 0. And I just want to loop n minus 1 times again, right? Because that is the number of partial sums that I have collected. So let me loop again for j equals 0 to n minus 1. So I take the product and then I add the partial sum at the current index. Okay, and it is a custom not to write begin and end when you are mentioning only one line. So here my for statement has only one line, so there is no begin and end. From here on out, I could return the value of p. So this should also be relatively easy to understand. Just for you to remember again, the first pass involves collecting the partial sums and the second pass involves summing them together and returning the product. And both the addition and multiplication algorithm that we looked at here today are analogous to the pen and paper method that we already know. So it's just a usage of some fancy terminology, but you should be able to handle this easily. Okay, so that is the content for this video. In the next video, we'll be looking into the division algorithm and the modular exponential algorithm. And I expect those algorithms to be a little bit more involved and challenging, but those are also going to follow the same patterns like we did here. So looking forward to see you guys in the next video. And please feel free to ask any questions that you have. It's easy to miss a step or two in these algorithms. That said, I'll see you guys in the next one. Have a good day and bye.